This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today is common ion effect in the ionization of acids and bases and hydrolysis of salts and pH of the solution. So common ion effect in ionization of acids and bases. So when there is ionization of weak acids and bases, so here the ionization of acid and bases that you are seeing, that is basically for weak acids and bases. We do not discuss ionization for strong acid and bases because that is 100% complete. But when it is weak acid and bases, it is not 100% ionization. So mostly it remain in undissociated state, but some percentage of weak acids and bases, they remain in ionized state, and we are talking about that only. So when there is ionization of weak acids and bases, if there is already some common ion, then what will be the effect on this ionization? Now, according to Le-Chatelier principle, if there is any common ion present when there is ionization, so obviously it will be affected and ionization will be hindered. So as a result, what will happen? The reverse direction, that is from right hand side to left hand side, that direction, the equilibrium in that direction, that will be increased. So phenomena in which degree of dissociation of any weak electrolyte, that means we are talking about weak acids and weak bases, that is suppressed. Suppressed means it is hindered. It is not so facile process when there is any common ion. So now the degree of dissociation, which we denote by the term alpha. So this alpha, that will be, the value will be less when there is some common ion. So that definition is the phenomena in which degree of dissociation of any weak electrolyte. Actually, here we are talking about acids and bases, but this weak electrolyte, it may be for any other compound also, that we will see later. But right now it is only for weak acids and bases. So when it is suppressed by adding a small amount of strong electrolyte, so the common ion that we are getting, that is basically coming from some strong electrolyte, but that is in very small, that is containing some common ion. That effect is known as common ion effect. Okay, so in this case we will take the example of weak acid. Which weak acid we have taken here? We have taken very common example, which is acetic acid. Now acetic acid, as it is weak acid, so its dissociation to H plus ion and acetate ion CH3CO minus, obviously it is not very high. But suppose there is already presence of some small amount of this salt, which is sodium acetate. Now when we are talking about salt, this is always fully dissociated. Okay, so here complete dissociation of this salt, but it is taken in small amount obviously. Here from the arrow you can understand this is single headed arrow, that means it is complete process. Equilibrium is involved in the second case, which is weak acid. But when we are talking about any salt, sodium acetate, here dissociation to sodium ion and acetate ion, that is common. But here the common anion is this part, which is already NCERT. Now because of this acetate ion, which is already generated from the salt, sodium acetate, now the dissociation of acetic acid to H plus and to acetate, this process will be hindered. Now it will be less compared to the previous situation. So this is known as common ion effect. Here small amount of sodium acetate, that is hindering the dissociation of acetic acid. Now here if we see this dissociation constant of acetic acid, already the amount of acetate ion is very high. Now we know that K is affected only by temperature. So as long as temperature is fixed, this K value cannot be changed. But we have already high concentration of acetate ion because of this common, because it is common. So that is why, to keep the value of K fixed, that is the numerator concentration of acetate ion, that value should be fixed. So that is why this equilibrium, now it will be going towards reverse direction, so that the value of K remain fixed. It is only dependent on temperature. Here acetate ion is the common ion, and hence its concentration is increasing, right? To keep the value of Ka constant, the concentration of these acetic acid molecules is increased. Now, sorry, the concentration of, just ignore this line. Actually, the line will be to keep the value of Ka constant, the concentration of acetate ion must be decreased, and that is only possible if we are moving in the reverse direction for the second equation, okay, not the first. So Le-Chatelier principle, equilibrium will be shifted towards left hand side, that is the reverse direction. So in this way, ionization of acetic acid is suppressed by the addition of this salt, which is containing some common ion. It may be also for potassium acetate or ammonium acetate. One common ion must be present, that is the conditions. Then only we can say common ion effect is there. Now here one more thing we have to notice, as the acetic acid dissociation is now suppressed, so just to keep acetate ion fixed, but another point is also there. In this way, the amount of H plus is also decreased. So when the amount of H plus is decreased, the pH of the solution is suppressed by the addition of sodium acetate, and as a result, when H plus is decreasing, that is acidity is decreasing, that means pH of the solution that will increase. That means it will be going towards basic side. Compared to the situation when sodium acetate is not present, then the pH, and when sodium acetate is present, under that condition the pH obviously it will be different. So when there is common ion effect, because this acetic acid dissociation is inhibited, so that is why pH of the solution will increase. Fine. So this example we have taken weak acid, but this is also possible for weak base. So we will take one example for weak base. So here we have taken ammonium hydroxide as the weak base, and here equilibrium is present. Its dissociation to NH4 plus and HO minus, it is partial, not full. We have taken this strong electrolyte salt, which is NH4Cl, and this is the common ion, right? So just like the previous case, here Kb value, that is the base dissociation constant value, which is for this equation obviously NH4 plus in the right hand side and HO minus concentration divided by the undissociated NH4OH concentration. Now as this amount of this ion is increasing, so to keep the value of Kb fixed, now the equilibrium that will be shifted towards left hand side, that is the reverse direction. Here NH4 ion is the common ion, its concentration is increasing. To keep the value of Kb constant, the concentration of NH4OH molecules is increased. So what it means, as it is going towards reverse direction, that means NH4OH that will increase, because NH4 plus is increased. So if NH4OH is also increased, then only Kb value will remain fixed. Or another way you can think that equilibrium is shifting towards left hand side, that means more amount of NH4OH that will remain in undissociated state. So that is written in the second point. Then according to Le-Chatelier principle, equilibrium will be in the left hand side from right to left, and in this case, as this dissociation is of NH4OH is hindered, so HO minus concentration that will also fall. So when it is falling, that means pH of the solution that will also decrease, because now HO minus concentration is decreasing means what? It is going towards more acidic side. Going towards more acidic side means pH of the solution that will decrease. Okay. So this example, which is for weak base, and another example we have seen that is for weak acid. So that is all about common ion effect in ionization of weak acids and bases. Next topic is hydrolysis of salts and pH of the solution. So we have seen different examples of salts until now. Just in the previous two examples, remember, we have seen already two salts. One is sodium acetate, another one is NH4Cl. So these are the examples of salts. And we also know what is neutralization reaction. Neutralization reaction is basically forming this type of salts. So neutralization reaction is reaction between acid and base, and salt is formed. So in general, how we write it, acid and base, we are getting salt, and also water is produced. Now when water will be produced, if acid and base it is containing H plus and HO minus, then only it is possible. Not any Lewis acid or Lewis base type of acid base I am talking about. I am talking about acid and base where H plus is present and HO minus present. Then only we can say that neutralization, after neutralization, salt will be produced and water will be produced. Now, this is neutralization. But if you consider the reverse reaction means suppose you have taken some salt, you are adding it to water, then acid and base produce. So the reverse reaction is basically the hydrolysis of salt. Reverse of neutralization reaction is hydrolysis of salt. So salt formed by neutralization, now they will ionize in water and they will produce acid base, and this acid base, that is from this acid and base, there will be formation of some cations and anions depending on whether this acid and base they are weak or they are strong. Both possibilities are there, right? So these cations or anions, they either exist as hydrated ions in aqueous solution, or maybe they are interacting with water to reform corresponding acids or bases, and that depends upon the nature of salt. So from these acid and bases that are produced after hydrolysis of the salt, these cations and anions, they can be remaining as hydrated ions. So suppose there is NaOH. Now NaOH, this is strong, so there will be full ionization like Na plus and HO minus, and this Na plus that will be surrounded by different water molecule where oxygen will be donating electron towards this. So it will be surrounded by several water molecules where oxygen is facing towards sodium. Similarly, HO minus that will be surrounded by water molecule, but now the positive part of water, which is hydrogen, that will be interacting with this. So in this way, Na plus ion will remain in hydrated state, and HO minus that will all can remain in hydrated state. Now that is only possible if there is full depending on the cation and anion. Okay, so that depends on the nature of salt. Now the process in which cation and anion or both the ions, that is both cation and anion of the salt, react with water and they affect the acidity or basicity of the solution. In that case, we consider, that is the discussion that we are going to do, it makes some sense. Where it is simply hydrated by the water molecule, that case we are not talking about. When there is cation and anion, both the ions, they are reacting with water and they are affecting the acidity or basicity to the solution, then only this discussion of hydrolysis it is possible. Now, how many types of salts are there, that we will see all the examples. Basically, there are total 4 types of salts possible. So these 4 types of salts, we will see some examples here. So the first type, it is combination of strong acid and strong base. So when you have taken some strong acid and base, the salts that you are getting, we have 3 examples. Sodium chloride, which is made from HClNaOH, then potassium nitrate made from HNO3KOH, then sodium sulfate made from H2SO4NaOH. Okay. Here we have strong acid and weak base combination. Strong acid, we have taken HCl and NH4OH, which is, that is ammonia. Its aqueous solution is basically ammonium hydroxide, and we are getting this salt. Then HCl, ferric hydroxide, we are getting FeCl3. Then lead nitrate, which is made from HNO3 and PbOH. Then we have H2SO4 and COOH. Sorry. Okay, so in this way we are having the second category of salts, which is made from strong acid, weak base. The third category will be weak acid, strong base. So from weak acid, strong base, three examples we have here. Sodium, potassium acetate, it may be sodium acetate also, depending on what you have taken. That is, in this place, if you take NaOH, it will be sodium acetate. Then potassium formate, formic acid and KOH. Then carbonic acid, which is weak acid, and sodium hydroxide, we are getting sodium carbonate. Both these H2 replaceable. So 1 H2CO3, 2 NaOH, we can get sodium carbonate. Now the fourth category, the fourth possibility is both are weak. That is also possible. So when we have taken weak acid, weak base, both are weak. We have ammonium acetate example. Then we have taken formic acid and H4OH, we are getting ammonium formate. We have taken carbonic acid and ammonium hydroxide, we are getting ammonium carbonate. Okay, so these are the four types. Number 1, 2, 3 and 4. Next, what we will do, we will talk about hydrolysis for all these four different types of salts one by one. Fine. And we will also see how it is affecting the pH of the solution, because the topic is first hydrolysis of salts. It may be any of these four salts, and as a result of hydrolysis, what is the effect of pH? It may be increased or it may be decreased. Okay. The first combination is salt of strong acid and strong base. Salts formed by neutralization of strong acid, strong base, they are actually neutral in nature. Now, why we are saying so? Suppose you have taken NaCl. So when you are doing hydrolysis, there will be formation of NaOH and HCl. Now, these two are strong, right? So there will be full dissociation of NaOH to Na plus and HO minus. Similarly, from HCl, there will be full dissociation of H plus and Cl minus, right? Now, if it is happening, then it means what? Here, from 1 mole of NaCl, you are getting 1 mole of NaOH and 1 mole of HCl. So it is 1:1. Similarly, from 1 mole of NaOH, you are getting 1 mole HO minus. From 1 mole HCl, you are getting 1 mole H plus. That means here concentration of HO minus total amount, that is equal to this. And when that is so, obviously the pH is not affected. Another important point is here the cations of the strong bases, which is this type of metals, very active, and anions of the strong acids. See, these are the anions from strong acid that we get, HCl or nitrate. So they, what happens, they simply get hydrated. There is no hydrolysis. Okay, because when I am saying that HCl is very strong, basically the ions that you are getting, that is actually very stable. Why it is stable? Because they are surrounded by water molecules. So when conjugate base is stable, then only you can say the acid is very strong. So when acid and base, they are strong, the corresponding conjugate acid or conjugate base, they are actually very stable. So why they are stable? Because they are simply hydrated, so there will be no hydrolysis. And the solution remains neutral because they are HO minus and H plus, both are actually same. And that is the reason that H plus and HO minus, as these two concentration are same, so they are also called, that is this type of salts are also called, 3 to 4 examples you have seen in the previous slide. So this type of salts we call neutral salt because they are solution that will be produced after hydrolysis. The pH will remain stable. So there is no acidity, there is no basicity. Example is NaCl, another example is KCl. So in this case, there is no effect on pH of the solution. But next two examples we will see, that is strong acid, weak base, and weak acid, strong base. So in those cases, there will be effect on the pH of the solution. Okay. So next category, number 2, weak acid, strong base. This is also known as anionic hydrolysis. Now, why it is anionic hydrolysis? You will be you will have that idea within few minutes. So salts formed by neutralization of these two combination. Example we will take here, sodium acetate. So sodium acetate, if I am hydrolyzing it in water, what I will get? I will get acetic acid and NaOH. So this is the combination we can. Now acetic acid, as it is weak, there is no full dissociation, so its dissociation will be partial. But for NaOH, the dissociation is basically full. Okay, so in this case, if I am writing the corresponding anions after dissociation, that I will get, and here I will get after dissociation Na plus and HO minus. So this is fully dissociated. Okay, and in this side I will get after, that is if I write the ions. Now Na plus, and it is simply hydrated and it is also common on both sides, so I will simply ignore it, and water will be there as it is present in large excess, right? Now you can see here these two, that is acetic acid, from this molecule we are getting acetate ion and H plus, but as it mostly remains in undissociated condition, very few percentage of acetic acid is basically remains in dissociated condition. So that is why these two together I will write like this, as if CH3COOH, and in the left hand side I will write acetate ion and water. Okay, so if I am writing this, then this example is only for sodium acetate, but in general if I am considering any weak acid strong base combination, then how I will write it? I will write it in this way. Suppose this ion I am writing as H minus plus water, then equilibrium, and this will be written as HA. Okay, and sorry, HO minus I have forgot to write here. So HA and HO minus. So this equation is the ultimate equation which we will be using for weak acid strong base combination. And now you can understand why it is anionic hydrolysis, because ultimately we have only the anion A minus. So this part, the part which is coming from the weak acid, we are basically focusing on that part, because the other part is coming from NaOH which is fully dissociated. So focus on this equation, that is the last equation written in blue. Acetic acid being a weak acid remain unionized in the solution. There is increase in the concentration of HO minus. So as you can see in the right hand side we have HO minus. So that is the reason why the solution will be alkaline. So when there is hydrolysis of weak acid and strong base combination type of salt, the pH is basically increased. It will be going towards alkaline side, right? Next, we will see some more derivation. That is, there is a formula for calculation of pH of the solution, and to derive, that is detailed derivation is actually not required as per syllabus, but if you are interested, so that is why I will discuss that. So here we also have this another expression which is required for the final derivation of the formula of pH. So here we have the expression K, which is for this equation that we have just last written. So K is equal to concentration of acid, concentration of base divided by salt concentration and water concentration. Okay. Now acid and base, that will be produced after dissociation, because we are talking about hydrolysis of salt. So salt and water, we are getting acid and base. Now if you consider this general equation, This is the corresponding equilibrium constant. Now water is present in large amount, so the concentration of it is not changed with time. So if you bring it to the left hand side, these two combination, it will produce a new equilibrium constant where the subscript we are using H. Now H is coming from the term hydrolysis, KH. So this is known as hydrolysis constant. This is also equilibrium constant, but we call it hydrolysis constant. So hydrolysis constant is basically concentration of acid, concentration of base divided by the salt concentration. Okay. Now some more derivation we have to see. So this equation, remember that I have already written in the last slide, A minus. Now we will do the discussion in terms of general equation, not sodium acetate, because this is true for any salt which is generated from this combination, that is weak acid, strong base. So this is the general equation. A minus anionic hydrolysis reacting with H2O, it is producing HA and HO minus. So initial molar concentration, that is in terms of molarity, suppose it is C, and these two are 0 initially. But when it has reached equilibrium, now we have written C common 1 minus H. Now what is H? Now remember, degree of dissociation, we write it in terms of alpha. So H is basically the same thing as alpha, but here we are using some different terms, not alpha. We are using the term H because we are discussing hydrolysis reaction. So instead of using alpha, we are now using H. So CH amount of A minus will be consumed in this dissociation. So the remaining amount of A minus is C minus CH. That means C common 1 minus H. Now as these two are 1:1 relation, that is 1 mole of A minus will produce 1 mole of HO, 1 mole of H. So that is why when CH amount is dissociated, obviously CH will be the hydroxide ion concentration and also the HA concentration. Okay. So degree of hydrolysis H, it is the fraction of total number of moles of a salt. Salt means this A minus, that is hydrolyzed at equilibrium, and it is called degree of hydrolysis, denoted by H. So this degree of hydrolysis, you can also write it, consider this ratio. This is the number of moles of salt hydrolyzed at equilibrium divided by initial number of moles. So this is basically the percentage. And if you simply multiply with this ratio, if you simply multiply 100, you will get the corresponding percentage value of H. Same thing as we have done in case of alpha, nothing new. Okay, only the term is different. Otherwise, it is the same thing. Now KH we will write in this way. Concentration of acid and base, that means these two, HA and HO minus divided by A minus. So this is the expression for hydrolysis constant KH. Next we will write two more expressions. One is for KW, another one is for KA. Remember KW, ionic product of water. This is H plus concentration and HO minus, that you already know. And if you simply consider the acetic acid dissociation, the corresponding Ka, that is dissociation equilibrium constant for acetic acid, in this case acetic acid, it may be in weak acid. So weak acid is HA, general formula HA. The expression we already know, it is H plus A minus divided by H. So these three basically, Ka, Kw, Kh. Combining these three, now we will get some new expression. Okay, so individually make it clear that you understand what is Kw, what is Kh, and what is Ka. Fine. Basically Kw, Ka we already know. Today's discussion we just have this one new term which is Kh, right? Now if we take the ratio of Kw and Ka, take Kw divided by Ka, then what will happen? These two will be cancelled and the remaining terms will be like this, which is nothing but the expression for Kh. See, same as Kh. So we are getting a new relationship between these three, which is this one. Now if it is true, then in place of KH, what we can write, KH is already equal to this ratio, but KH we can also write as if it is HO minus concentration, HA concentration, that means CH, then divided by A minus concentration, which is just simply use this from this equation. Okay, so CH divided by C common 1 minus H, C cancelled. Ultimately, KH is equal to CH square divided by 1 minus H. Now, if it is true, now the expression for H, what we can write? We can write as if it is KH by C. Why? Because with respect to 1, H is very small. So 1 minus H, it is almost equal to 1. So ignoring this value as if it is equal to 1, so KH is equal to CH square. That means H is equal to root over KH by C. But KH we already know it is KW by KA. So instead of writing KH, you can write KW and KA, this ratio. So ultimately we are getting the relationship between H and right hand side we have KW, KA, C. KH is no longer present. Now from this equation, we can derive the expression for pH. So pH of the solution now we can find how. Remember Kw is equal to H plus and HO minus. That means H plus is Kw by HO minus concentration. But in terms of HO minus, I can write CH. Remember in the previous slide we already seen this concentration is basically CH. Now why we are writing CH, there is a purpose for that, because ultimately we will replace H with this value, because we have already proved in the previous slide that H is equal to this. So instead of writing H, you can write this value. So finally, the concentration of H plus you are getting in terms of Kw, Ka and C. Now if you take negative logarithm in the left hand side, you basically get pH. And in the right hand side, you have three terms. Kw, we already know its value at 25 degrees centigrade. We can also have from database what is the value of Ka, that is the acid dissociation constant. And C is basically the concentration of the acid. So once you know these three, you can easily calculate the pH of the solution. So next step what we will do, we will take negative log both sides. And if we do so, negative log left hand side we are getting basically pH, and negative log in the right hand side. Because of this root, there will be half term. All the negative will be gone because we are now replacing each of them in terms of pK. So pKw, pKa and log C. Now half pKw, that is basically 14 by 2. So 14 by 2, 7. So that is why it is written 7. And this part is, it will remain as it is. Now depending on the value of Ka and C, the pH may be different terms. But one thing you have to notice, that it will be always greater than 7, right? Because these terms are positive. Fine. So, and concentration, this is obviously not negative. pK value, that is also not negative. So there is no negative term. Everything is positive. So obviously it is greater than 7. So this is the formula for pH which you will actually require, not the detailed derivation. I have just showing the derivation in case you are interested. Otherwise it is not required. You just need this final expression for pH, because that you have to use in the problem given. Next combination is strong acid and weak base, and now we will call it cationic hydrolysis. Okay, in the previous case it is anionic hydrolysis, not is cationic. Salts formed by neutralization of strong acid and weak base. Example, we will take NH4Cl. They are basically acidic in nature. In the previous case, you have seen pH is increased, it is basic, now it will be acidic because it is combination of strong acid, weak base. Effect of acid is high. Now NH4Cl, it is made from NH4OH and HCl. It is being a weak base, it will remain ionized in the solution and there will be increase in the concentration of H plus because HO minus is concentration is not so high. So that is why pH will be towards acidic. And this will be the final expression for pH. But how we are arriving it, that will derive. And here one interesting thing you can see that pH is equal to 7 minus half pKb. In the previous formula, you have seen everything, there is no negative sign. And pKa is there. But now as it is cationic hydrolysis, and we will focus on the base mainly because that is the weak base. So pKb term will be there, not pKa. And here we have negative sign and these are basically positive. So it will be lesser than 7. Whatever is the pH, it will be lesser than 7. Okay. But how we are reaching this expression, that we will obviously see. Now, just like the previous case, I'm jumping some steps. So NH4 plus, that will be ultimately remaining. Cl minus is cancelled. And in the right hand side, we will have H plus and undissociated NH4OH. Now this will be the expression from NH4Cl, but I will consider the general expression which will be B plus as if it is equivalent to NH4 plus H2O BOH. Okay, so if you are doing so, then the expression for hydrolysis constant, that will be H plus BOH. You can compare with the previous case, it is more or less same, only in place of B plus there was A minus. So see here B plus is involved, so that is it is cationic hydrolysis. Okay, so this is KH. KB will be equal to B plus, that is simply consider the dissociation of BOH. So similarly, just like the previous case, now also we can get a relationship between KH, KW and KB, just like previous, nothing new. So this is the expression we are getting. Okay, and H is equal to root over KH by C. That is also we have already seen in the previous case, same thing. So H will be, instead of writing KH, if I write KW by KB, it will be like this. Okay, so this is H. Next, concentration of H plus, that is basically equal to CH, right? Now in place of CH, I will write C into H, this expression, that means KW by KB into C. Now this C, if I bring inside, it will be C square and ultimately the term will be KWC divided by K. Okay. Now both sides, if I take negative logarithm, both sides if I take negative logarithm, ultimately it will be negative log H plus, which is basically pH. Directly I will write all the expression. So half KW, if there is half pKW, that will be basically 7, that is 14 by 2. So directly I am writing 7. Okay, then sorry, it will be plus, only this part is negative because C is here, KB is in the numerator. So final expression will be half log C, sorry, it is negative Why it is negative? Because when you will take negative log before C, it is still log C. We are not taking any pk term. Remember in the previous case also, C was present in the numerator. Okay. So when we have taken, sorry, it is log C, there is already positive sign. But in this case, there is a negative sign because it is present in the numerator. So that is why there will be negative, and KB, it is also negative because in the it is in the numerator. So when you will take log, the negative sign will still be there. So it will be half pKb. So final expression that we are getting, which is this one. So this formula you will use when there is a combination of strong acid, weak base in the salt for which you are considering the hydrolysis. Now the last combination, this is basically the combination of weak acid and weak base. Now basically it is both cationic hydrolysis as well as anionic hydrolysis, right? We will choose this combination, and now the question may arise. In the previous two cases we have seen pH is either that is greater than 7 or less than 7. But now what will happen? Now both are weak. Now what happens? Whether the final solution will be acidic, basic or neutral, that depends on the nature of the acid or base, depending on their pK value and pKb value. And in this case, the formula for pH that we will get finally, you will see in that formula, both the terms pKa, pKb, both are involved. In the previous two cases, you have seen either pKb involved or pKa, but now both will be involved. The cation and anion formed undergo hydrolysis, forming weak acids and weak bases. Weak base, both. Fine. The degree of hydrolysis H, in this case, you will see it is not dependent on the concentration of the solution. In the previous case, we have seen the KH value, it is dependent on concentration. See, H value is dependent on concentration. In the other example also, we have seen this is dependent on concentration. See, H is dependent on concentration, right? So if that is the case for these two, but here you will see H is not dependent on this. Now we will derive it. Though it is the example we have taken, but ultimately the equation we will write in general form. We will write both the acid anion and cation. So it will be BOH HA. Okay. So in this case, initial concentration for these two, suppose it is C, these two are 0. Finally, it is consumed amount is CH. So both remaining amount is CH. These two are CH. Fine. So the expression for KH, that will be concentration of these two. That means CH into CH divided by concentration of B plus and A minus. So it is C common, C square and 1 minus H. So ultimately what we are getting, H square divided by 1 minus H whole square. This is the expression we are getting. So KH is basically equal to H square if we are ignoring this term, because H is very small with respect to 1. So it is almost equal to H. Now H is equal to root over KH, right? Now KH, if you consider the relationship with KW and relationship between KW, KA, KB and KH. These four terms now we have to consider. In the previous case, you have seen KH is related to either KW, KA or KW, KB. But in this case, all these three terms will be considered. And if you write all the expression of these, and when you will take the ratio of KW divided by KA and KB, you will see this ratio is basically equal to KW. That means now in place of KH, what we can write? We can write root over KW divided by Ka into Kb. Okay. So here, until this it is clear. Okay. So H should be equal to root over this Kw, Ka, Kb. So next step what will be, we will try to calculate what is the pH of the solution. So one thing is clear, degree of hydrolysis is independent of the concentration of the solution. So here you will not see any C term present in the expression of pH. So the last statement, that is clear. Next we will find out what is the pH of the solution. So pH of the solution for the combination of weak acid, weak base combination, right? So for this, what will be the pH? First we will write the Ka expression, which is H plus K minus divided by HA. If it is so, then H plus is equal to Ka multiplied by HA divided by K minus. Why we are doing this? Because now in place of HA, I will write CH. Remember in the last slide, HA is basically CH, right? And divided by A minus is C minus CH. So I will write here C common 1 minus H. Now that is equal to H by 1 minus H, because these two cancelled, right? So Ka is equal to, okay, one thing we have to notice, in the previous slide we have already proved that KH is equal to this. That means root over KH, that should be equal to H by 1 minus H. Okay. Now if this is true, now in this H divided by 1 minus H, in this place I can write root over KH. Okay. So this expression ultimately we are getting for H plus. Now one relationship we have also proved, which is, remember in the previous slide we have proved what is the value of KH. We have already proved the value of KH is Kw, Ka, Kb. So as KH is equal to Kw, Ka, Kb, so H plus we can write as if it is equal to Ka root over, that is from this we are writing. Okay. Next we will do negative log both sides. Okay, simply first I am taking log, so there will be half common. Ka will be inside. So if KH, Kw, 1 minute, I'll just check it. Kw divided by sorry, this is KH. This here. Okay. Now if we are taking this Ka inside, then it will be Ka square. So ultimately Ka square divided by Ka, it will be this type of expression. Okay, so one mistake is there. Now if we take half common, and obviously with log Kw log Ka minus log Kb, because Kb in the numerator. Now if we take negative sign, it will be pH half log Kw. It is basically minus half log Kw, which is nothing but pKw divided by 2. Then negative log Ka, which is basically pKa. So pKa divided by 2, and there is already negative, and we are taking another negative, but for this new negative it will be simply pKb, but this negative sign it will be still there. So this is the ultimate expression we are getting. If we take half common, it is basically pKw, sorry, 7, this part is 7, half common. So this is the final expression. Remember in the okay, here I have not shown it. This is the final expression for pH. Here important point is, depending on whether Ka is larger than Kb, or Kb is larger than K, depending on that you will get some value from this part. So it may be a negative value, it may be positive. If it is positive, that means when Ka is greater than Kb, it will be something positive. That means it will add to 7, so pH will be greater than 7. But if pKb, if Kb is greater than Ka, reverse case. This is one case. In that case, pH is greater than 7. But if Kb is high, then this part will be negative and it will be something lesser than 7. So it depends on the value of Ka, Kb, whether the final pH value, it will be acidic or basic. So now overall result, okay, this is also written here. pH is equal to half pKa minus pKb. The pH of the solution can be greater than 7 or less than 7 depending on pKa and pKb. So whatever we have derived today's class, this is the final expression. Strong acid, strong base, that combination we are not we have not here, because it will be ultimately neutral, no question of no change in pH. But when it is strong base weak acid combination, which is also known as anionic hydrolysis, in this case KH, and this is the most important expression, then we have pH value greater than 7, and here we have, for the second case, 7 minus half pKb, half log C, pH is less than 7. And when it is weak acid weak base combination, now in the expression for H, there is no C term, that is, it doesn't depend on volume or concentration. And this is the final expression for pH. It is almost neutral because that is, though it may be lesser than 7 or greater than 7, but ultimately it will be more or less in this range, which is almost neutral. If it is suppose 6.8 or if it is 7.9, you cannot say it is very basic or acidic. So it is almost neutral, it is around 7. And when it is strong with strong acid, hydrolysis is not possible, no question of hydrolysis. Okay, so these formulas you will mainly need as per syllabus, but also some more extra formulas are also there in case you need. Okay, so we'll end today's class. We'll end the session here. Thank you for listening.